Hi. Today we are going to talk about Lecture 19, Learning Objective 8. We're going to be looking at when we can break the octet rule, either having an expanded octet or having fewer than that octet. So we've got three main exceptions to the octet rule. We're going to have ions or molecules with an odd number of electrons. And when I say ions, I'm usually meaning polyatomic ions, right? Because we always do our Lewis structures for our molecules. So when we have those odd number of electrons, we're obviously going to have at least one structure or one atom within the structure that does not have 8 electrons. We could also have atoms with less than an octet. And of course, atoms with more than an octet. Okay, so let's look at odd number of electrons first. So here, these are really rare. And generally they are unstable and reactive. So let's look at some examples. So these are generally going to contain chlorine or nitrogen. So we've got ClO2, NO, NO2, and O2 minus, which are all examples. So let's draw this out. For ClO2, we get the following structure. Right here. Here we have a negative charge here, and a +2 charge here. So you can see this is a very unstable, unhappy type of structure. NO doesn't have any formal charges in it, but just like the example above, we have something that does not have an octet. And in both of these cases, we see that the thing that doesn't have the octet is the more electropositive. Chlorine is less electronegative than oxygen. Nitrogen is less electronegative than oxygen as well. NO2. Here we have a positive here and a negative here. And again, here's where we're lacking the octet by one atom. And then O2 minus can look like this or like this. You'll see it's both. And here we have something that is lacking, and then well, expanded and then lacking. So probably this one would be the more likely option. Okay. Next exception is when we're going to be lacking an octet. So we have fewer than 8 electrons. So this is going to be things that are either in the first period or the first part of our second period. So elements in the first period. Well, elements from the first period. Aluminum and boron are also two that are going to not do an octet. So for instance, hydrogen, obviously, only going to have 2 electrons. Helium, only 2 electrons. And then boron and aluminum. Will actually form structures where we only have six electrons around the boron and the aluminum. And these are stable structures. It's really only boron aluminum that you have it with, but what you see is if you try and get an octet with these, for instance, if you move one of the electron pairs into a bonding site, you get a positive formal charge on a fluorine, which is horrendous, and a negative formal charge on a boron, which is also horrendous. So these are too close to, well, these are fairly metallic in nature, aluminum and boron, so they are not going to produce structures like this. So these are unstable. Okay. So generally, if you are filling the octet of a central atom, and that results in a negative charge on the central atom, and a positive charge in the peripheral atom, and you have the option to not fill it because it's aluminum, boron, helium, or hydrogen, then don't fill it. Just leave it with lacking an octet. Okay, our last exception is an expanded octet. So greater than 8 electrons around our central atom. And this is just for elements in period 3 and below. So these are ones where we have those available d electrons or available d orbitals. So because we have these d orbitals, we can make additional bonds or hold additional electrons. Okay, so an example of this is PF5 and XeCl4. So let's look at both of these. So PF5, we obviously are going to have an expanded octet because we have 5 atoms around a central atom. And when we draw this out, it looks like this. Where we have our central atom that has 10 electrons. But if you were to actually do formal charges, you find that none of the atoms in this structure has a formal charge. xenon as well. If we were to draw its structure out, xenon tetrachloride, it would look like this. And again, here we have a structure where we don't have any formal charges, but we have 12 electrons around the central atom. Okay. Last thing I kind of want to bring up is the idea of drawing a bond dipole. So a bond dipole is a way of indicating polarity within a bond. So here we're going to have a separation of charge, and that separation of charge is indicated by that dipole. So separation of charge that produces a dipole or electric dipole, and we use a bond dipole to show that. So we have to have a polar bond for this to work. Okay. And we can think about bond dipoles a lot of times like a vector. So it's going to have direction and magnitude. However, we draw it the opposite way that we do an actual vector. With a vector, you're going to be pointing your arrow towards the positive. Here, we're actually going to be pointing our arrow towards the negative. So we have an arrow, and it points towards the more electronegative atom. And then it's going to have a plus sign at the end of the arrow over the more electropositive atom. Okay, so let's try and look at this. So if we have something like a oxygen-hydrogen bond, here we have a bond dipole because we have electronegativity difference of 3.5 minus 2.1, which is equal to 1.4. So it's above that 0.4 threshold. So we have a bond dipole. We have a polar bond. Our oxygen is more electronegative, so we're going to point our bond dipole towards the oxygen and then a plus sign by the hydrogen. So it could be above, or you could write it below like I've written here. Doesn't really matter. Like that. Okay. That's it for this video. I'll see you guys in the next one.